This is topic 4.5, solving related rates. So let's go ahead and take a look at this first question. If y squared equals 3x to the fourth plus 6x, find dy dt when x equals 1 and dx dt equals 2. Now, I want to make sure you understand. We want to find dy dt when these are equal to those values. We cannot plug those values in until we take the derivative of every term with respect to t. So let's go ahead and give that a try. 2y dy dt is equal to 12x cubed dx dt plus 6 dx dt. Now, what we're looking for, I usually like to highlight. So we're looking for dy dt, okay? So we're looking for dy dt. In fact, I'll go ahead and change that color. We're looking for dy dt when x is 1, dx dt is 2, and let's give that a try. So we have 2, and I don't see a value for y. So I'm just going to leave an open parentheses there because that's sort of my to-do list. dy dt equals, and let me put that highlighter there for dy dt, 12, and x is 1, and dx dt is 2, plus 6 times 2. So what do you notice? We don't have y. So if we come over and we take a look, when x is 1, going back into our original equation, we have y squared equals 3x to the fourth plus 6x. So plugging in x equal to 1, we get y squared equals 9 and y equals plus or minus 3. So you know what I'm going to do over here? We're going to use the value for when y is a positive value, okay? So we're going to take y equal to 3 since y is positive, and that will be noted next time. So here's y is 3. If you have a situation going on where something is getting larger or smaller, you'll know which one to choose. In this case, I should have specified that. Okay, so now we go ahead and solve this. 6 dy dt equals 24 plus 12. So dy dt is equal to 36 divided by 6, which is 6. Okay, let's go over some guidelines, and there's no units on that, so we just leave it like that. The very first thing you want to do is draw a picture, and we'll be doing that every single time. Of course, we didn't have a picture here. We were just doing some practicing. We want to make a list of all known and unknown rates and quantities, okay? We need to relate the variables into an equation. Remember, we're studying related rates. Then we will differentiate with respect to time. So everything is the derivative with respect to time. And then we'll substitute the known quantities and rates and solve. So if you notice, we're going to do the substitutions after differentiation. And there's a little note here, substituting a non-constant quantity before differentiating is not allowed. And I do want to make something a little bit more clear. If a quantity is not changing, then the derivative with respect to t is going to be 0. So we need to make sure that that makes sense. So it shouldn't be that big of a deal. Okay, let's go. The width of a rectangle is increasing. Okay, so you know what I'm going to do? I'm going to draw a rectangle real quick. I think the best way to draw a rectangle, to solve these problems, is to draw a picture. So I have a length of my rectangle and a width. And it says that the width is increasing. And it says that the length is also increasing. Let me just put it in one end. Whoops. Let me get a smaller eraser. Okay, so the width is going up and the length is going up. And let's talk about what we want to find. They say that the width of a rectangle is increasing at a rate of 2 centimeters per second. So they say that dw dt is equal to 2. And I'll put units on my answer, but usually when I work these out, I don't. And its length is increasing, dl dt, at a rate of 3 centimeters per second. Okay? At what rate is the area of the rectangle increasing? So they want us to find dA dt when W is 4 and L is 5. Now, you know W and L are changing. So we want dA dt at the moment those are happening. I don't know if that makes sense right now. Maybe it will be, but they're not. None of the sides are constant, so we cannot plug any values in until after we take the derivative, okay? So the area of the rectangle, you have to look for an equation that relates the variables, okay? So we need an A, a W, and an L. So the area of any rectangle is the length times the width. So dA dt is the derivative of L with respect to t times W plus L times the derivative of W with respect to t. Okay? We are looking for dA dt, and dL dt was given as 3. And they wanted when W was 4, L was 5, and dW dt is 2. So this equals 12 plus 10 is 22. And of course, we're going to have square centimeters per second. Now note, area is centimeters squared, time is seconds in this problem. Use your units to come up with your final answer. It will really help you. Okay, let's see if we can try our next problem. This should look familiar. We did a short one of these in a previous example, but we didn't have values at that time. So a police car approaching a right-angled intersection from the north is changing. So here's our police car, and that police car is coming from the north. And he is now moving, from a speeding car that has made the turn, and he is now moving east, okay? So what do you notice first? You should notice that Y is getting smaller and X is getting larger. That would be the first thing that I would make note of. That this distance here is going to eventually be here over time. Over time, it's only going to look like that distance. So Y is changing by getting smaller, and X is changing by getting bigger. And let's put a Z over here, okay? So let's read the rest of the problem. When the police car is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with a radar gun that the distance between them and the car is increasing at 20 miles an hour. If the police car is moving at 60 miles an hour at the instant of measurement, and that means when they're measuring all of this other stuff, what is the speed of the car? Okay? So we want the speed of the car is dx/dt. So we want to find dx/dt, and because this is the speed. And speed is always positive, so even if this was getting smaller, we would give the positive value for speed. So find dx dt when the police car is 0.6 miles north of the intersection. So that is when y is 0.6. And it also says, and the car is 0.8 miles to the east. X is equal to 0.8, and when dz dt, that's the distance between them, is equal to 20, and they sure give us a lot of information here, dy dt is equal to negative 60. So why did I have dy dt equal negative 60? If the police car is moving at 60 miles an hour at the instant of measurement, so the police car is moving in the negative direction, getting smaller, going down. We talked about that. But basically it's negative because the change in y is small, because y is getting smaller. Its change is negative. Okay? So what is the relationship we have here? You can already see that it's going to be x squared plus y squared equals z squared. Now, all of these sides are changing, so we have to take the derivative. 2x dx dt plus 2y dy dt equals 2z dz dt. Let's see if we have anything missing. 2 times 0.8 times dx dt, and dx dt is what we're looking for. Plus 2 times y, which is 0.6, and dy dt is a negative 60, equals 2, and then we don't have z. So let's keep it open, and we will make sure we find that in a minute. And then dz dt was given to be 20. So what I want to do is come over here and find z. So at the moment, or when, at that very moment, when x is 0.8 and y is 0.6, let me move that down a little bit. So it's only at this moment when x is 0.8 and y is 0.6, x squared plus y squared equals z squared. So 0.8 squared plus 0.6 squared equals z squared, and you will get 1 equals z squared, so z is 1. Okay? So you find that at that moment what that is. And if you go ahead and multiply these out, I got 1.6 times dx dt minus 72 is equal to 40. And if you solve that, you'll get dx dt is equal to 70. And it's miles per hour, but let's just look at this. X is in terms of miles, right? These are miles. And time is in terms of hours. So we have miles per hour. So that concludes this video.